What's today? 25. Amina, good morning. And good morning, Oscar and Louisa. Good morning, Alicia and Fini. Good morning, Alex and Errol. Good morning, Chelsea. Good morning, Lola. Good morning, Ellie. Good morning, Bella. Good. That was pretty quick. All right. Well, we got most of you. I'm going to set this aside. We're meeting today, this week, folks, and Wednesday. We won't meet Thursday because I've got MSAs all day long. Let's begin with you first and see if you have some questions on chapter probably 2 at this point, problems. So, are there any you've done you'd like to talk about together? Here, I'll get you back in the studio a little more. Squish myself here towards the whiteboard. So any chapter 2 questions. What we're going to do after that is pretty much finish off chapter 2, start chapter 3 if we have some time. So we'll see how it goes. So let me know if there's some you've marked in your book and you'd like to see, get some help on those. If not, it's okay. We got lots to do, as per usual. I got one. Okay, good. Let's see it. So page 179. And Antonin is here too. Good morning. And it's 21D. So everybody turn to page 179, and I'll get there as well. Let me mark down that I've got my Antonin here also. And away we go. Okay, 21 is a whole bunch of partial pressures versus time for a reaction between A and B gas to form C, all right? And they got gas A is present in excess. Okay. Well, C is probably the one that's going up, isn't it? And A and B are the ones going down. Okay, so let's see. Write a balanced chemical reaction for the equilibrium in the question. Okay, that was A. B, write the equilibrium expression, Kp, okay. Calculate the numerical value for Kp for the expression. And then finally, D says calculate the Kc value for this reaction. Okay. So we had this last week, and let's try it together and see how it works. Remember, there's a relation between Kc, C for concentration, and Kp. This means they're proportional. And I never remember the thing, so I'm going to flip back a couple pages and find it. We wrote it down last week, and there it is. And it goes like this: Kp, and while I'm writing, I can ask, and Sophia's here, good, super. Alicia, while I'm writing, can I ask you what's the answer to C? If you could type that in, that'd save us a little time. And in the meantime, it's Kp equals Kc times RT, change in N. Okay? All right, so here we go. Thank you very much. All right. Super. So she's got a Kp value of 0.60. And remember, Ks have no label, so we don't have to worry about that. And I want the Kc. And the R that she puts in is probably which one? Ba-dum, ba-dum, ba-dum. Let's see, it's got to be R and T. So it's got to be the 0.0821. I know I round that a little different than she does. Okay, 0.0821. Later atmosphere per mole Kelvin times the temperature. And do they give us the temperature there? Hope so. Well, they don't give us the temperature, so we're going to assume that it's standard temperature, as far as I know. So let's see. They really don't give us the temp. Well, that's kind of a mistake on her part. They should give you the temperature. Okay, let's assume like 25 degrees, so let's say 298 Kelvin. Hope everybody's with me. I'm just writing madly here. We all right? Okay. And the final thing here is the change in number of moles of gas. So we talked about that last week. So change in moles of gas. Well, we do have a change here, don't we? We got A and B making C. So I got A plus B going to C. Now, I don't know if it's 1 to 1 to 1. I got to look at the data and see. Okay, so that's going from 0 to 1.5. These are going from 4 down to 2.5 and 2.5 down to 1. So I'm guessing, and we'll see if Alicia agrees, when you did the balance reaction, is it just 1A plus 1B equals 1C? Because that's kind of what I would guess. And for others too. In other words, does that look correct to you? If I didn't wipe it away. Thank you, Alicia. Okay, so what that means is what, gang? What's the change in moles of gas? If I go from 2 to 1, what's the change in moles of gas? So everybody take a guess. I know it's early. Try and wake yourself up. What's the change in moles of gas? It's going from what to what? So what is this going to be? Delta M. What's the change in moles of gas going from reactants to products? Everybody type in a guess. No, no, no. Still waiting for a correct guess. Believe me, I'm happy you're guessing. And no, no, no. Still lots of incorrect guesses. Ah, Alicia, -1. Oscar, -1. Why? Because it's going from, it's the gas. Here, let's write this out. Okay, so it's the moles of gas of the products minus the moles of gas of the reactants. Makes sense, doesn't it? Don't we always do products minus reactants? So it's 1 minus 2, so -1. So, gang, you got to do 298 to the -1 power. Yes, I know it looks weird. That's life. So crank all that out, and I'm hoping that you get then the right answer, Alicia and others. I'll leave you with the rest of that calculation. Okay? So unless there are questions on this, okay, are there other ones that we'd like to ask about in chapter 2? Any other ones in chapter 2? That's a really good thing, probably to memorize. And star. You're welcome. Any others? I'll give it another minute, and then we'll turn to new stuff or stuff we haven't covered yet. It's related to stuff we did last week, so it's all pretty good. Okay, then we're going to go to my notes first and do a little review. And my review. Penelope's here. Thank you for checking in. I got almost everybody. That's beautiful. Everybody but Aiden, I guess, unless Aiden checked in or I didn't see him. Okay. Okay, Okay, last week we talked about pressure and how it affects reactions. So what we're going to do is we're going to say that we're going to decrease the pressure in each of these reactions, and you're going to tell me which way it shifts, towards the reactants or products. So our stress, as Cheryl would say, is decreased pressure. So we're going to give you 3 reactions, A, B, C. And the results of the stress will be, you're going to tell me which way it shifts, towards the products or towards the reactants. Okay? All right, here we go. First one is 2CO2. That's, of course, a gas. Forms 2CO. Come on. 2CO gas plus O2. And I'll say shifts to where? Okay, next one. H2 plus I2. And I2 is a gas here. often it's a solid at room temperature. So it must not be room temperature. And it makes 2HI, kind of a happy little molecule. Friendly at least. And that's a gas as well. And then the final one is H2 gas plus I2 solid this time. So probably at room temperature. Forms same friendly gas 2HI gas. Okay, so go ahead and write that down. Okay. Remember we talked about the change in number of moles being important for you to see at a glance and think about what it means. Let's do A together. Generally, I got what? 2 moles of gas on this side, 3 moles of gas on the other side. If I had solids or liquids, I wouldn't care. It's only the moles of gas that matter. So 2 and 3. So there's going to be an effect of this stress of changing the pressure. That matters then if there's a different number of moles of gas. Okay, so the easiest way I remember is if I increase the pressure, it wants to take up less space. So I increase the pressure, and it's going to squeeze to the side that takes up less space. But notice what my stress is. My stress is decreasing the pressure. So in this case, it's going to take up more of which, well, it will shift to which side. Yeah, thanks for participating. Now take a guess, everybody. Shifts towards reactants or products there if I'm decreasing the pressure. I got a lot of correct guesses. Good. The brains are clicking. I like it. It's going to go to the products, the side with more moles of gas. So it takes up more room if you ease off on the pressure. So if I ease off on the pressure, more of these can probably break down and form these guys. Good. Look at number 2 and take your guess on number 2. Which will it shift to, reactants or products? So for B, I should say, not number 2. For B, which way will it shift, towards reactants or products? I'm going to wait for a few guesses. Nope. Can I give you a hint? 1 plus 1 is 2. 2 is 2. Now try and guess again. Exactly, Anne-Sophie. Therefore, if it's 2 to 2, there you go, Chelsea. So there's no effect. In a sense, it doesn't change any of the movement of making more products or making more reactants. Does that make sense? If it's the same number of moles of gas, it won't get squished more on one side or the other. It won't be pushed by pressure. All of them will be squished by the same amount on both sides. Right, it doesn't have to shift. So in this case, it doesn't shift. All of them would get more concentrated. They'd all be squished in a smaller container, but I wouldn't make proportionally more of the HI side as opposed to more the other side. It would just stay the same relative amounts. Cool, huh? Okay, now you guys' turn again. So look at C and take a guess on C. So I'm decreasing the pressure. Good. The brains are turning on. Thank you, everybody. Correct. So, Chelsea, Amina, Alicia, it is indeed to the products because I'm going from 1 mole of gas, that's a solid, to 2 moles of gas. So if I release the pressure, it will make more of the side with more moles of gas. So more products will form. Okay? To reduce the stress of decreasing the pressure. Yeah, it's okay. All right, are we good? Okay, what we didn't get to last time, and we're going to begin with now, is just a quick look at what happens with temperature. Okay, so here we go. Temperature effects. Exactly. Right. Exactly, Louisa. That's why it was that answer. Okay, temperature effects. Here's sort of the bottom line. Bingo, Amina. Good. Okay, so for temperature, an increase in temperature favors an endothermic reaction. And by favors means more product forms. When I use it in this sense, okay? So here, favors means more product forms, or it goes more in the forward direction. Let's look at a reaction and think about it a little bit. So, as an example, let's take I2 gas. Yeah, okay, got it. I2 gas going to 2I, that's it, gas. So breaking up an I2 into 2 I's. And the delta H for that, the change in heat, if I can write an equal sign today, is 151 kilojoules, okay? Well, already, is that endo or exo? Who remembers this? If it's a positive delta H, is it an endo or exothermic reaction? Endo, endo, endo. Thank you, Alicia, Penelope, Bella, Anthony, and others. It is indeed endo. That's important here. So we know that if we do certain things, well, it'll affect it. Okay, so let's start with that then. So here are my stresses. So my first stress is temperature is increased. And the shift, so shifts to, so what would you guess? If I increase temperature, it shifts to which side? If I increase the temperature, it will shift to which side? Hmm. Okay, no. So let me see if I can help you think about this. If I agree this is endothermic, what that means is I could write this into the equation, couldn't I? And if I wrote it in, I would write it on the reactant side. So I would say I2 gas plus 151 kilojoules. Sorry, I got to write small. Well, what you can do then, folks, is you can really think of this as being, it's not a chemical, but it's going to work like this. If I add more temperature, so to speak, if I increase the temperature, it's like I'm putting heat in on this side. And if I put heat in on the side that has heat written in the equation, the stress will try and use that up. So the equation is going to try and use that heat up. And to do it, it's got to go towards the, as a few of you figured out, it's got to go towards the product side to use up that heat. Another way you can think of it to help you is, hey, I2, it's got to break into pieces. Here's an I2. It's got to break into pieces. And at high temperature, it's going to do that more anyway, right? So I'm going to break it up more at a higher temperature. And there it is. The broken up side will be favored at a higher temperature. Another way to think of it. Okay, let's do a couple other stresses. So that's about temperature. Let's do a couple others as review. So B, the container is compressed. What will that do? So take your guesses now. Which way will it shift if I compress the container? So I'm going to compress the container. What will the effect be? Shift through product to reactants. Good, Bella and Chelsea. Yes, because I'm going from what? If I increase the pressure, I want to go to the side with less moles of gas. Which side has less moles? This side has 2 moles. That has 1 mole of gas. So indeed, towards the reactants. See how that works? If I increase pressure, I go to the side with less moles. If I decrease pressure, it goes to the side with more moles. Think of them relaxing. Ah, we got more room. We can make more moles. If I squish them, they're going to make less moles of space. So that's the side with less moles, the reactant side. Good. Exactly. Good. Several of you got that. Thank you for participating. Here we go. See the last one. Let's just say that we do this. I atoms are added. Think of the demo we did when I was at school for Le Chatelet's principle with the colored ion, right? The dark brown stuff or brown red stuff. So here I'm going to add I atoms, and which way will that drive this to relieve the stress? Which way will it drive the reaction? So adding I atoms will shift it which way? Take your best guesses. I know it takes a while for your guesses to get from me to you. No, you to me. Ooh, I got a mixture. Not really a very good mixture. Okay. Gang, we're adding these guys. Look at them. They're on this side. I'm going to dump in a bunch of these. The reaction is going to tend to try and use them up, right? The Chatelet's principle. It will tend to compensate for that stress to relieve it. And the only way I can relieve this stress is to go this way and use them up. So it ain't going to shift towards the products. If I add these, right, if I add a product, it's going to try and use it up and shift towards the reactants to use it up. Yes, I know I'm adding more product, but it's not about adding, it's about what does that adding cause the reaction to do. Let's see if I got any questions here. Yeah, so to speak, and Sophia, I'm adding them on this side. That's correct. That's where the I is. The others are I2s. Okay. Any other questions or comments from you on that? We still have one more demo, and I may try and do it at school Wednesday. We'll see if I can get a room to do it in, because they got MSAs on Wednesday. But for now, we've got some other stuff. I noticed that I didn't finish up in chapter 2, so we're going to do that right now. We're still doing okay on time. I got some notes to myself. We need to talk briefly about page 113. Come on, book. Here we go. Okay, so there's some basics that I haven't told you about, but they're not hard. Flip to page 113. Maybe it's obvious anyway, but we need to mention it. Percent yield. Means what percent do I make? What percent do I change the reactants to products? What percent are reactants changed to products? Mathematically, it's going to make complete sense to you. So it's essentially in the past you've learned that it's the products formed divided by the I don't even want to write that. Okay. I don't want to write that. I want to write what it is here. Okay, because then I know what I'm talking about. So percent yield can also be written this way, and that's what I'll do. Really what it is, it's the actual yield divided by the theoretical yield. Okay, and that's times 100. Now, we did problems like this earlier in the year where we had a limited reactant problem, and I would say, okay, well, what's the yield? How much do I actually get to make? And we said, oh, well, it's the lesser of two amounts of the reactants that Well, if they go to products, the lesser amounts of those products. Okay, this is about percent yield, and I'm going to give you an example. Okay. Paper burning. It's close to 100%, if not 100%. Hey, if you burn paper, it pretty much all burns, okay? Let's talk about dissolving plastics, like a plastic cap thrown in the ocean. Plastic cap dissolving. It's close to 0%. You know, love may or may not be forever, but plastics are virtually forever. That's why they're so awful for the ocean. So theoretically, I could have some kind of reaction to dissolve plastics. I could do it. I can have a theoretical yield. But the actual yield, the amount of plastic caps that actually dissolve, is so minimal that it's virtually zero up here, is making the whole fraction zero. Whereas here, the amount of paper burning theoretically is the same as what it actually does. So it's pretty much 100 or close to 100% yield. Okay? That's what's up with that. Now, in terms of language that I've been using with you about favored, so let's do percent yield. And if I go from 100 to 0, this would be where, and there's 50. This is where I would use the term reactants are favored. And if it's over 50, that's where I'm going to say the products are favored. Okay? I hope that makes sense to you. So it's over 50%. So less than 50, reactants favored, greater than 50, products favored. That says percent. I know my writing's awful. Percent yield. Percent yield. 0, 50, 100. On the upper side, products favored. Lower side, reactants favored. Good. Still looking at what I skipped. Page 127. So I think we had this. Oh, let's do that real quick. Let's do that real quick. That was page 117, by the way. If I didn't write that. Okay. Now let's pick up one other tidbit. And the other tidbit is on page 127. And essentially, I just want to comment on a graph that Cheryl has. And it's a PE diagram, I think. And she has this. And is that an endo or exothermic reaction, gang? If it's a PE diagram, these are Down here it's time, or you can just say stages of reaction. So endo or exothermic. I will blow my nose while you consider this. And I got lots of correct answers. Thank you, Chelsea, Alicia, Bella, Amina, Penelope, and Sophie. It is indeed an endothermic because I end up at a higher potential energy than I start with. Okay, so here's the scoop. From here to here, is the EA, the activation energy for the forward reaction. But if you think about it, on this diagram, you can also get the EA for the reverse reaction. So that would be here. So this, from there to there, would be the EA for the reverse reaction. Right, so if I'm coming from this side, then really my molecules have to achieve less energy to get all broken up before they go back to the reactant side. Remember, right, reactions can go forward or reverse, a lot of them. So new AP idea, forward and reverse. So reverse, I need this much energy to break them up. Forward, I need this much energy. Obviously, a lot more for this particular reaction. We don't know what it is. It doesn't matter. Okay, let's do her other diagram and talk about it here. So it's percent of the collisions. And this is energy. And it's more like kinetic energy, really. She calls it collision energy. I'm going to call it kinetic energy. And you had this diagram before. Okay, I got some low energy collisions. I got a lot in the middle, and I got some that are higher energy collisions. And the point is, what? She's got that wrong. No, she doesn't. Okay, all right, sorry. Here's my question. Check out this diagram. Which molecules need more energy? Collision energy, we could call it, or kinetic energy. Which ones need more kinetic energy to break up? The ones on the reactant side or the product side? Which need more energy to break up? Let me say that again. Which needs more energy to break up? Reactants on the reactant side or product side? Exactly. Good. Alex and others, reactants is correct. So what that means is I'm going to use the same blue color. So I need the same activation energy on this diagram to be plotted out here. So I'm going to say EA forward. But what that means is then for the other one, and this is kind of interesting. So in other words, all of these molecules would have enough energy to do the forward reaction. But for the reverse reaction, it's easier. So that line would be lower. So I would have a lot more energy, a lot more molecules available. So let's say that's EA of the reverse. So I got a lot more molecules that could potentially react and do the reverse reaction. Okay? That's all I'm trying to say there. Anyway, I thought that was kind of a cool graph, so I wanted to look at that with you. I like those two diagrams of hers. Just seeing if there's any questions, and then we have one last thing, which is page 138. Okay, there's the rub. Now, you there? Okay. The last thing that's new out of this chapter, I don't know why she put it in this chapter because it really belongs in the next chapter. It's page 138. The last section we're going to talk about is 2.4, and it's about entropy. You had enthalpy, which was heat of reaction, but entropy, okay? Well, what is it? Well, it's more or less this. You ready? This would be low entropy, okay? Low entropy. That would be high entropy. So it's kind of like the amount of what? Oh, man, that was really high. It went all over the place. God, it went out of my studio. Out of my 1 meter studio. What a big mess. So entropy is kind of like what? Not just energy, though often a higher entropy does have a higher energy, true. No, it's not necessarily energy. Entropy, think of how they look. There was my low entropy. Entropy is disorder. Maybe like some of your rooms if you haven't cleaned it in a while. Yeah. Disorder. So how random is it? Now, here's a cool thing about the universe. The universe is a constant battle between two things. Here's a little philosophy for you, okay? Universe. It's a battle between minimum energy and maximum disorder. Well, let's call it what it is, maximum entropy. The minimum energy, we've already talked about, that's called enthalpy. It's the heat of a reaction. The maximum entropy is the opposite. Now, the cool and interesting thing is these two desires. Let me give you an example, okay? Here we go, minimum energy. Okay, it's sitting on my hand, it's pretty low energy. Maximum entropy would be maybe it flying around the room. I know, not really going to happen in this case. Minimum energy is going to rule. On the other hand, if I have steam flying around this room, it's going to stay that way. It's not going to come and sit on my hand, not unless I make it very cold. So steam at room temperature, that's going to be more on the entropy side. That's going to win. So one side or the other, I say the universe, the way I was taught it, which I think is fun, is the universe has two desires. Desires. Minimum energy, maximum entropy. Let's look at a reaction, and I think you'll see what I'm talking about, okay? Let's look at a really simple reaction. Example. Take some salt, right, from your salt shaker. NaCl solid. And dissolve it in water. So I got NaCl aqueous. Which side is more minimum energy? label the side. Which side is more minimum energy? Just take your guess. Which side would be more minimum energy? Where are particles moving the least? Solid or aqueous? The reactant or solid side, right? So this is minimum energy. If we can close our eyes, now imagine the little salt ions cruising around, mixing with the water. So that's definitely maximum energy. Or if you like the other words, we can say that this is more an example of, no, I don't want to do that. Okay, all right, so sorry. I went back on what I was thinking. Okay, for you and I, to make this happen, I got to break up the solid a little bit. So I got to add heat. And my friends, anytime you add heat, it's going to be to the minimum energy side. Makes sense. Heat plus minimum energy makes more randomness. Okay. So heat plus minimum. In other words, these are always on opposite sides. That's more random. That's more minimum energy. Let's do another reaction. You can tell me which is which side. Okay. Here's a reaction you may not have seen before. Calcium carbonate solid forms calcium oxide solid plus CO2 gas. I want you to label it. Which side is minimum energy? Which side is maximum randomness? Maybe you can just type that in for me. Shorthand it if you want. Min energy is bara. Randomness is bara. Tell me which side is which. Which side would be which here? And you'll see eventually why I want to train your minds to think this way. It's very useful for the next chapter. Essentially, we're already doing chapter 3. This is really chapter 3 stuff. Bella says minimum energy is the reactant and the product is maximum randomness. Minimum energy is product. So we got a difference of agreement. No, minimum energy is a reactant. And so you two are in agreement, Anne Sophie and Bella. Any other guesses? Okay. All right, not so many guesses. Okay, here we go. The solid here is definitely a minimum energy state. And I got two things going on this side. I got two products. That's more random. And one of them is a gas. And gases are very random. So this is definitely maximum randomness over here. Or we could say the products have more entropy disorder. Have more entropy. And if I had to add heat here, I'd have to add it to this side, wouldn't I? To break it up to make this sort. In fact, gang, what sort of reaction is this? This is what family of reactions, just to review the word. This is a reaction. What kind of reaction is this? Let's get a few more writing later. What kind of reaction is this? This is a reaction. Yes, it's endo, but that's not what I mean. As a type of reaction, if I got a chemical going into parts, what kind of reaction is this called? Thank you, Bella. Exactly. Alicia, good. It's a decomposition reaction. One thing is decomposing into two. All right, that's review, just for fun. Good. Let's see if she gives you some letters here. If she does, I'll do it, or I'll wait till we get to chapter 3. But yes, she does. That's cool. Okay, so turns out entropy as with the little zero, and the little zero, remember, means standard temperature, or we can say standard condition. Standard condition. Do you guys know that? CX stands for condition. It's a good abbreviation. AP Bio does that too. And it's in kilojoules per mole Kelvin. Kind of a weird label. You've sort of seen it in the Pivnert, that kind of label with the R value. Oh, and I wanted to say up here, my little hint for the world. Psst. More gas particles, more entropy. Not a big surprise because gases are more disordered, right? Okay, I can get the actual entropy as a number by doing what? I can do the entropy of the products. So entropy of products looks like SPROD, but it's not. So S of the products minus the entropy of the reactants. And the way this actually ends up is a plus sign ends up being increasing entropy. And a minus ends up being decreasing entropy. Or more orders, another way to think of it. Decreasing entropy. I'll abbreviate that. Yeah? Okay. And you can get data and just plug it in. I can get a product minus a reactant and or products minus reactants, and I can get an actual value for the entropy. So to round this out, we can say, kind of like we did with temperature effects earlier this hour, a greater temperature tends to favor the side. I don't know about tends, I think it always does. Tends to favor the side with greater entropy. Think of my example, okay? You can think of that being low temperature. If I throw them all over, then that could represent high temperature if they're molecules, right? Chunk of calcium carbonate, low temperature, break it up into parts. That's going to happen at a higher temperature. So greater temperature favors the side with greater entropy. Ute! You're done with chapter 2. Hooray! At least the notes. So get busy on chapter 2. I'm going to send to you chapter 3. So those of you that are really into it and are caught up and everything, I'll have it due after break. But if you want to start it now, you may. No, I don't want you to work all break, but I do want to give it to you ahead of time in case you'd like to start it this week. Some of you are probably pretty set with chapter 2 already. Okay? I'll put a reasonable due date on it. I'll send it to you digitally. I'll do that today because I'm going into school a little bit to where I have that file. All right. I hope you're all well. Stay healthy. For Aiden, if he's not there, I will put this on the live stream in Google Classroom for him. Okay. See you Wednesday, but not Thursday. Fare thee well.